Hi and welcome to the next lecture of the course Evolutionary Dynamics, and so far we have been spending time on capturing the three tenets of any evolutionary processes, which is reproduction, selection and mutation. We have already completed our discussion on reproduction, and today we will continue our discussion from where we had left off last time, talking about selection. So, let us pick up our discussion from where we had left off last time. What we have are two bacterial species, two distinct genotypes A and B, which are constrained in an environment such that their total numbers are set to be equal to a specified number k, which is the carrying capacity of the environment. And now these two distinct genotypes are growing at different rates A and B. In our last lecture, we had derived the dynamical equation which represents the change in frequencies or the fraction of the total population that belongs to genotype A and genotype B, and where we had left off was trying to comment on the stability of the two steady states associated with the dynamics of this system. So, we will pick our discussion up today from where we had exactly left off last time. So, let us just start by recapturing our scenario that we have an environment E. This environment has a carrying capacity equal to k, and we have two distinct genotypes of bacteria in this environment, genotype A and genotype B. And the constraints that we are working in are x A plus x B is equal to 1, where x A and x B, as we defined in the last lecture, represent the fraction of the population that belongs to genotype A and B respectively. And then we differentiated this equation to get the result dxa by dt plus dxb by dt equals 0. The right hand being a constant, its derivative gives us a 0, and which gave us this result that the rate of change of the fraction of individuals which belong to genotype A is exactly equal to and opposite in sign to the rate of change of individuals which belong to genotype B, and hence this result. And when we used these two results to derive the dynamical equation associated with the system, we ended up with the equation dxa by dt equals x A times 1 minus x A times A minus B, where A and B are the growth rates associated with the two genotypes capital A and capital B, and this is the equation for which we want to comment on the stability of the two steady states associated with it. So, let us take our discussion forward, and if we look at the equation, the first thing that we had discussed last time when it comes to analyzing stability of steady states is putting the derivative term equal to 0, and that gives us the points, the values associated with x A, where the rate of change of x A with time is equal to 0. So, when we plug dxa by dt equal to 0, but we know dxa by dt is equal to x A times 1 minus x A times A minus B. We are working under the assumption that A is greater than 0. This is the growth rate of the bacteria with genotype capital A. B, which is the growth rate of the bacteria with genotype capital B, are both growth rates. So, these are non-zero positive quantities, and also that there is a distinct difference in the speed at which these two species grow, these two genotypes grow. So, A is not equal to B. Hence, A minus B is either greater than 0 or less than 0. So, this is a non-zero quantity. So, dxa by dt is only equal to 0 when either x A is equal to 0 or 1 minus x A is equal to 0, which implies x A is equal to 1. And these two quantities, x A equal to 0 and x A equal to 1, are my two steady states associated with this system. after having determined the steady states associated with the dynamical process, the next step when it comes to commenting on the stability of these steady states is plotting the dxa by dt against the variable xa, and first identifying where are the steady state points on this curve, and then disturbing the system and checking which way does it move when we disturb it from a steady state in one direction or the other. So, let us just do it, but as we had identified, there are two distinct cases for doing that in the case that we are dealing with. So, case 1 is when A is greater than B. This represents the case where genotype A is growing faster than B. And when we think about the biology of this problem, if we have two bacterial genotypes A and B, and A is growing faster than B, you would imagine biologically, if we were to imagine this process in our head, you would imagine that eventually all of A should take over and the genotype capital B should get eliminated. That is what biology, microbiology associated with bacterial growth tell us, and really the math that we are deriving only makes sense if that also leads us to the same answer which we know to be true physiologically. So, we want to plot xa versus dxa by dt, and this curve we had discussed last time for A greater than B looks something like this. This is xa equal to 0, this is equal to 1, and there are two steady states xa equal to 0 and xa equal to 1, and we want to comment on their stability. So, again just as we had done last time, let us look at xa equal to 1. Now, if I disturb the system to the left, I bring it slightly here. What I want to check is what is the sign of dxa by dt when xa is not at steady state value, but slightly to the left of steady state. And I note that slightly to the left of steady state, the sign associated with dxa by dt is positive, which means xa increases as time increases, and hence the system wants to move towards increasing values of x as we move forward in time. So, approaching from the left hand side, if we were to introduce a disturbance to the left of xa, the system wants to move back towards the steady state from which it was disturbed. And what happens on the other side, if you introduce a disturbance which is to the right of steady state value 1, at this point the sign associated with dxa by dt is negative, which means as t increases, xa decreases, and hence upon introduction of a disturbance which moves the system to the right, the system wants to move to the left. So, we see that on introduction of a disturbance on either side, the system wants to move back towards the steady state that we disturbed it from, and hence xa equal to 1 is a stable steady state. So, this is a stable steady state. And to comment on the stability associated with the second steady state, we are only going to disturb it towards positive values, because xa, the variable that we are dealing with, is fraction of the population belonging to a certain genotype, and negative fractions does not have any physical connotation in the system that we are talking about. So, we are only going to disturb it towards the right hand side and see where the system takes us once that disturbance is introduced. So, when we introduce this disturbance to the right, we note that dxa by dt is positive on the right hand side, and hence if the system is at this state, as t increases, xa increases and system moves towards the left, which means away from the steady state that we had disturbed the system from, and hence this is an unstable steady state. So, that completes the mathematical analysis for the case 1, but now let us try and take a look at this system and see if this makes any biological sense or not. We knew from biology of the problem that we are dealing with that when A is bigger than B, then the A genotype should take over the B genotype, and hence the fraction of the individuals that belong to genotype A should go towards 1 and B should get eliminated, and hence fraction of the population which belongs to genotype B should go towards 0. And that is exactly what this graph is telling us. It tells us that as we go forward in time, if we have any XA, the system moves towards the right and it approaches XA value of 1, which is the entire population belongs to genotype A, and XB, which is just equal to 1 minus XA, gets eliminated and approaches 0. So, this does make a lot of biological sense. Now, let us take a look at the second case, which is where small a is less than small b, where genotype A is growing slowly as compared to the genotype B. So, again we do it the exact same way. We have small a less than small b, and we are going to plot the same graph. But now I leave it to you to convince yourself that whenever small a is less than small b, the shape of the curve is just going to get inverted from what we saw last time. So, in the previous case, when small a is bigger than b, we have an inverted parabola, and I leave it to you to convince yourself that when small b is greater than small a, the parabola inverts itself. So, the shape of the curve at this point is going to look, okay, I want to use a different color. The shape of the curve is going to look something like this. This is the value xa equal to 0, this is the value xa equal to 1. And now, when we analyze the stability associated with these 2 points, let us look at xa equal to 1. When we introduce a deviation to the left, dxa by dt is negative, hence xa decreases as we move forward in time. The system moves in this direction. At x equal to 0, if we introduce a deviation to the right, dxa by dt is still negative, which means xa decreases with time as we move decreases as we move forward in time. So, any disturbance in this direction moves the system away from this steady state, and any disturbance in this direction brings the system back towards the steady state that we have started with. And hence, this steady state now becomes unstable, whereas xa becomes stable. So, as compared to the last result that we had, where xa was stable, now xa becomes unstable, and in the previous case where xa equal to 0 was unstable, xa equal to 0 becomes stable. So, all that has happened on switching the signs of a and b is that the 2 points have switched their stabilities. And let us also now look at the biology associated with this. When small b is bigger than small a, that means genotype B is growing faster than genotype A, then we imagine the biology to dictate that all of B cell types should take over the population and cell types belonging to genotype A should get eliminated. And that is exactly what we see in our results, where as we have this system, any space in this system, xa always move towards the value 0, which means the fraction of individuals belonging to genotype A moves towards 0, and xb consequently, which is just 1 minus xa, always moves towards 1. So, this makes a lot of sense as far as the biology is concerned, and that's what we want to discuss when it comes to selection between two distinct genotypes. But the problem is that the genotypes, multiple genotypes are going to coexist very often, and moving more than 2 genotypes is not trivial, and then the math becomes difficult, and simple analysis such as this is no longer possible when we have more than 2 genotypes associated. So, I will discuss one more simple technique to analyze the system when we have 3 genotypes. But first, let us just quickly write the equations associated with these 3. So, now let us imagine our genotypes are A, B and C. Their growth rates are A, B C. So these are genotypes, these are growth rates, and we have the same constraint that this growth is taking place in an environment E with a carrying capacity equal to K. So the individuals belonging to each of these three species, three genotypes, when added up give me a value equal to K. And again, just as we had done last time, we are not going to be dealing with distinct numbers, but we will be dealing with fraction of the population that belongs to genotype A, and we will call that quantity XA. The fraction of the individuals that belong to genotype B will be fraction XB, and similarly fraction of individuals that belong to genotype C will be XC, and XA plus XB plus XC will always have to be equal to 1. And when we differentiate with respect to time, we get dXA by dt plus dXB by dt plus dXC by dt equal to 0. And the consequent differential equations that dictate the dynamics of this process can be written as dXA by dt equals XA into A minus phi, where phi is an unknown just as we had done last time. dXB by dt is equal to XB into B minus phi, and dXC by dt is equal to XC into C minus phi. What had helped me last time when I was only dealing with two distinct genotypes is that when we derived the differential equations, there were two differential equations, and I also had algebraic relationship between those two variables such that XA plus XB is equal to 1. Now the problem that I have run into is that I have three distinct genotypes, hence I have three variables XA, XB, XC, and the algebraic equation between these three variables is XA plus XB plus XC equals 1, and I can no longer substitute one in the form of another and reduce my system to one differential equation in one variable only, which is something I was able to do when I was dealing with two species. That's the problem that I have, and hence to be able to solve this equation, these three equations have to be simultaneously solved and ensure that the constraint XA plus XB plus XC is always equal to 1. So these system of equations have to be solved either via a solver or if these are linear in nature can be solved analytically and the solution arrived at. So this is analyzing three species is not as trivial as how we had analyzed two species. But there is a useful way to represent dynamics of three species graphically, and that's what I want to talk about next. So three species, we have three variables XA, XB and XC, and the composition of this environment can be represented using an equilateral triangle. Let me call this A, B and C. I will explain in just a second why this has to be an equilateral triangle for this representation. Now, if the composition is at for any point P inside this triangle, inside or even on this triangle, what we want to do is we want to draw perpendiculars to the three sides. So perpendicular to the side AB looks like this, perpendicular to the side BC looks like this, and perpendicular to the side AC would look something like this. Let us call the length associated with these three perpendiculars as the one opposite vertex A, let us call it PA, the perpendicular opposite vertex B, let us call that PB, and the one opposite vertex C, let us call that PC. Let us also define a quantity in this equilateral triangle, which is the length of the perpendicular drawn from one vertex to the other side, and let us call that alpha. The length of this perpendicular is alpha. And equilateral triangles have this property such that if P is any point on the interior or on the edges of this equilateral triangle, PA plus PB plus PC is equal to alpha. This result holds independent of location of point P. This result holds independent of location of point P. The only constraint being that point P has to be inside or on the edges of the triangle, it cannot be outside the triangle. Once we have this, how does this help us? This result is very useful because it directly relates with what we have been talking about so far, because what I am going to do is bring alpha over to the other side and write this as PA by alpha plus PB by alpha plus PC by alpha equals 1. Now, you should begin to see some similarities between the result that we have here for our equilateral triangle and the result we have for our 3 species system XA plus XB plus XC equals 1. So, I am going to write this in this graphical representation of species. PA by alpha for any point P will represent XA, PB by alpha for any point P will represent XB, and PC by alpha for any point P inside this triangle is going to represent XC, which is equal to 1. And hence, I am going to use this equilateral triangle as a representation of where is my species located at any particular time. Okay. So, if P is an internal point, then this is how we just draw the perpendicular, and that will give us the consequent fractions of each type of genotypes which are present in the environment at that particular time. Suppose I want to represent in this triangle a composition of an environment such that XA is equal to 0.5, XB is equal to 0 and XC is equal to 0.5. So, you should check that XA plus XB plus XC is equal to 1. And how do we represent this point? The way to do that is, we know that XB is equal to 0. That means I want to locate a point P such that perpendicular to the side which is opposite to vertex P, its length is equal to 0. Because remember, the fraction of B individuals is given by the length PB divided by capital alpha. And if XB is equal to 0, which means PB has to be equal to 0. So, PB has to be equal to 0 means that point P lies on line AC. Right. So, this implies that P lies on AC. Again, what I am trying to do here is locate point P on this equilateral triangle, which represents the 3 species present in the fractions that we have talked about here. And now what we want next is locate a point P on this segment AC such that from that point P, the perpendicular drawn opposite the vertex A, so this perpendicular should be equal in length to the perpendicular drawn to the side which is opposite vertex C, which is this perpendicular. And that, from intuition, it should tell you that has to be the midpoint associated with the segment AC, because this is an equilateral triangle. So, given any composition, what we can do is we can find a point P which represents the composition associated with the distribution of the genotypes at that particular composition that we have specified. So, equilateral triangle is a useful way to represent when we have 3 or less than 3 distinct genotypes present in an environment. Unfortunately, scaling it up to higher number of genotypes becomes difficult because we are constrained by the number of dimensions that we can draw on a planar surface, and hence it is not possible. So, that concludes our discussion on selection in a bacterial population. In the next lecture onwards, we will start with the third tenet of our evolutionary process, which is mutations. Thank you.